I love maths, something that you will never hear anyone say out loud. But I actually do love maths, and while you may share this love for mathematics with me, it's unlikely that you'll ever feel comfortable declaring that love out loud in public or even to your closest friends. This is probably because mathematics, perhaps more than any other school-taught subject, is something so many people find so incredibly hard. And yet to some people it's so easy and so simple, appearing as if it was almost a second nature to them, similar to how an athlete, an artist, or a musician may be born with a biological unlearned affinity for their talent. So are some people really hardwired for maths while others are not? Where does mathematical ability come from in the brain, and how are some people able to move from the realms of high school mathematics to become professional mathematicians in the likes of Albert Einstein, Alan Turing, and Stephen Hawking? 3 questions I plan to answer in this video. My name is Hashem and I'm a forever tired medical doctor and University of Cambridge graduate who just happens to think that the human brain is kinda cool, very cool, which is why I make videos about it on YouTube. Take action and subscribe and you may just unlock your action potential. One of the most vivid memories that I have from my early childhood are the many hours that I spent stuck in the car in traffic with my parents. To entertain my incredibly bored mind, I'd look out the window and count just about anything from lampposts to billboards and red cars that were on the road with us. I always thought I was an incredibly weird child for doing that, and while there may still be an element of truth to that statement, counting is actually a universally human experience, one which is not even unique to humans. That's because many creatures around us can count and do count, as this brilliant 2016 study illustrates. In this study, these scientists designed an experiment where very young fish that had just hatched were given the choice to join either a group with 40 fish or a slightly larger group with 50 fish. The scientists discovered that the baby fish could compare the sizes of the two groups and were consistently able to select and join the larger of the two groups, in this case the group with the 50 fish. Because more fish in the group provide the small young fish with more protection from hungry predators. Basically, being able to count from an early age is an essential skill for many animals because it determines whether or not they will survive. We like to think of newborn human babies as being adorable idiots who know nothing and are good for nothing. And while it's true that they are good for nothing, they definitely know a thing or two about mathematics. Suppose you present a newborn baby with 2 cards, one with 4 kangaroos and the other with 8 kangaroos on it. The baby will immediately know which of the 2 cards has more kangaroos without needing to count. Scientists call this an approximate number sense that all humans have. In early childhood, it allows children to understand and manipulate small numbers with precision and large numbers by approximation, long before they've had any exposure to formal mathematical education. In fact, you as an adult make use of your approximate number sense on a regular basis. For example, if you look at this image, you will instantly know that the right-hand side card has more kangaroos than the card on the left-hand side. The difference, you're slightly better at this than a newborn, with the ability to discriminate up to a ratio of 7 to 8 rather than just 1 to 2. Kangaroos, of course, live in Australia, which also happens to be the home of several hundred Aboriginal tribes. Until recently, these tribes lived fairly isolated lives from the rest of humanity, having been sea-locked on the Australian subcontinent for more than 50,000 years. 2 of these tribes are the Warlpiri and the Anandaliakwa tribes. They're notable because these tribes don't have words or gestures for numbers. Why? Because they just don't count things. And as weird as that may sound to you, counting was just not a part of their culture or tradition as it likely was for you. Which is truly remarkable because when scientists tested children aged between 4 and 7 from these communities, they discovered that despite having never counted anything before in their entire lives, the Aboriginal children performed just as well and sometimes even better than the English-speaking children who had been exposed to counting their entire lives. All this indicates that except for select cases of acalculia, every one of us has mathematics hardwired into our brains like it's some sort of language. Because I suppose mathematics might be its own language after all. In 1943, French mathematician Jacques Hadamard asked his fellow mathematicians to describe how they manipulated numbers in their minds. Albert Einstein responded by saying that words and language, whether written or spoken, do not seem to play any part in my thought process. And almost 80 years later, we know that to be true, and we know why. The earliest evidence came from case reports of patients who suffered from aphasia, meaning that they could not use language to communicate. These patients frequently had preserved mathematical abilities, however. It was later determined through MRI studies that mathematics activates an entirely different brain network than that which is triggered by language, one which is only ever activated by mathematical thinking. The brain's math network is primarily made up of the interparietal sulcus on both sides of the brain, though the left-hand side appears to play a more significant role, and also the dorsal prefrontal cortex and the inferior temporal lobes. These three brain regions communicate with each other and also communicate with the hippocampus, where your memories of mathematical rules and the sort of information are stored, to turn a challenging mathematical problem into something more manageable. You hope anyway. And surprisingly, according to this study that was published just last week, there appear to be neurons that are specific to addition, and other neurons specific to subtraction in the brain's medial temporal lobe. Now, if you're still watching this video, I think at least some of you may be questioning the relevance of counting and basic arithmetic to more complex mathematics. But as it turns out, mathematics is a little like Jenga, in that more complex mathematical ideas or blocks tend to build up on top of more simple ones. Not only that, but to extend the metaphor further, your brain uses the same areas involved in counting and basic arithmetic, and recycles them to learn and solve more challenging problems. In other words, it takes one block from near the bottom to place near the top. And so, even if you happen to be utterly hopeless in maths, you still make use of the same areas of the brain used by Albert Einstein to arrive at his theory of relativity. But this leaves one question unanswered. How are great mathematicians made? And the truth is, no one really knows. It probably comes down to a combination of quality of formal mathematical training and an innate mathematical aptitude. There is shaky evidence, however, that newborn babies who are better at discriminating between the number of kangaroos on a card will grow up to have better mathematical abilities later on in life. More convincingly is the new research which suggests that the levels of two critical neurotransmitters in the interparietal sulcus, GABA and glutamate, can promote and even predict future mathematical ability during sensitive periods of childhood brain development. I'm sure you have your own ideas as well, so why don't you share these ideas in the comments below? And don't forget, take action and subscribe, and you may just unlock your action potential. See you all next week.